Okay, so now you understand how the output is calculated. So again, what do we have? We have these input vectors, which feed into the hidden neurons and compute using softmax the output value. And our training data tells us which values here should be 1. And we, just like before, we can now compute the difference between the actual output and the output that we expect. So if you go to the training data for the input canal, you expect an output value of 1 for the, grand, of, and Venice. So this is in the output vector, what should have a 1 and the other should have a 0. And then just like before, you apply the training algorithm to update all of these weights in the network. And then you do the next sample and so on until the overall error in this whole network is small enough. So now at one point you finished training these networks, the error is small enough. So now the question is, how does this network help us to get the word vectors? And the core idea you can see in the calculation here. So let's say we have our one hot vector as input. So there are 6 words in the input, and the second word is the one we want to have the word vector for. So we represented the 6 words using 3-dimensional word vectors. So you can see the 3 different weights for each input word, and for each of them we have 6 weights. So now you do the same calculation as before. You do the weighted sum input vector times weight matrix, and you can see, because you have a one hot vector, there's only one value in there that will be picked out of the matrix. Now all the other values here, they go to 0. It's 0 times 0.3 plus 1 times 0.6 and so on and so on. So now if you do this calculation here, you get an output vector in 3 dimensions. This is the vector that we want. This is our word embedding. So the 3-dimensional representation of this word here. And now if you look into the matrix here, you can see basically that this is exactly the second position in the weight matrix that we picked. So for each word, our 3-neuron hidden layer gives us exactly the word vector that we want as the end result. So what we do is we just take the weights from the hidden layer. These are our word vectors. So we are not really using this neural network. We spend a lot of time training it, but then we just throw away this output layer. What we're interested in is the hidden layer. Even though we are trained it using this output layer, we are not interested in the output. Now, this again is a large dimensional output, and we don't care about it. All we care about is this condensed weight vector here that we use for the word embedding. And that's actually a typical trick in neural networks. Like here, training a network and then just ignoring the output and using, in this case, the hidden layer as the end result. So why does this work? Well, this works because if you have a large enough corpus of words, you can see that different words that appear in similar surroundings will also have, will result in similar output vectors. If you have certain words that appear about sports or around cars or around travel, even though it's different words, the context will be similar. So this means that the output vector for these different words will also be similar. So essentially, what you are forcing the neural network to learn is a condensed representation in the hidden layer, so that even though the words are different in the input, they map to similar vectors in the output. So in other words, you get away from the surface form, like before we had this example of flammable and inflammable. if you have a large enough corpus, these two words will appear in similar surroundings with fire and flames and what have you. So even though in the input vectors, they are completely different because of the one hot representation, they will be forced into a similar representation in this hidden layer. One problem these word vectors don't solve is disambiguation. If you have words with the same surface form, like bank can appear as the river bank or the financial bank, then you're basically mixing together the context. So if you have lots of documents that talk about banks in the financial context, you'll have words of bank customers and accounts and money and so on. And then you have correspondingly words for riverbank. Yeah. And what these hidden layer will do is just mix these two senses together. So it does not learn that these are two different concepts which just happen to have the same surface representation. But still, even with this drawback, one thing we can now do is do this idea of math with word vectors, for example, for solving analogy questions. And one of the most famous ones that appeared a lot in blogs and news around the time that word2vec was the big topic was this example here. If you take king, subtract man, and add woman, the computer will say that now you have a queen. Similarly, you can start from Paris, subtract France, and add Germany, and suddenly you get Berlin. In both cases, the capital of the corresponding country. And it's interesting because now you can have not just some kind of reasoning, but also some kind of knowledge encoding. We can have knowledge about capital cities in countries in a knowledge graph. But here we just learned it from reading lots of, in this case, news articles. So we can also have some kind of reasoning using these word vectors. And you can do all kinds of other fun things. One thing that's more entertaining than useful is if you start from the fish word vector and add music, you come to a bass. And here you can see the problem with two different senses mixed together. Now you can have bass and bass, one the fish, one the musical instrument, but because they have the same surface form, adding music to fish, you end up with the word here. And there are lots of other fun things you can do. Now you can just take a road, subtract an ocean, but add a car, and then you come to a sailboat. Or you take a desert, subtract all the sand from the desert, but add suburbia. And what do you have? You have driveways. Or you take a dorm, take the students out of the dorm, and now you have a bachelor pad. Or you take a barn, remove the cows, and now you have a garage. Or you take a Yeti, remove the snow, add economics, and then you have the Homo economicus. So many of these examples I took from the website here, where you can find a lot more fun examples on these word vectors. Let's go back to training this network. In the beginning, I told you there are two different ways of training it. And the second one was the CBOW, the continuous bag of words approach. In this approach here, what we do is we take a window of words and we are sliding this window across the text. So this is our continuous bag of words here. And you can see we are sliding it one by one. So here the window size is 1, 2, 3, 4, 5, and we are sliding this 5 window across the documents. And I have the wrong example here. I'll just fix this for the slides that I upload. But yeah, this is the right one. So here is again our input sentence. But now the input, we have multiple words. So Claude Monet the Grand. Oh, sorry, this is actually okay. I think I just mixed up the two examples earlier. So, here we have our rounding context, Claude Monet, the grant, and we want to predict the target word. Yeah, before the word here was the input word, and now the word here is the target word, so the word that we want to predict in the output. So we have our context like Claude Monet, the grant, and the word we want to predict is painted. So this is the one that should go here. Or Grand Canal when is in, and then the word we want to predict is off. This is the one that has to go in between Grand Canal when is in. So now the input to the neural network is not a one-hot vector, it's a multi-hot vector. So we have a 1 for each word that appeared in the input, like Claude Monet, the grant. And this word painted is 0, and all the other words are also 0. And now on the output, again, we compute softmax. And what we expect here is 1 for painted and 0 for all the others. So in training, again, we can compute the error, train the network, update the weights, do this for all the multi-hot input vectors until the overall error of the network is small enough. And then again, we take the hidden neurons as our word embeddings, just like before. So both of them result in word embeddings in these n-dimensional word vectors. So you might ask which one is better. And well, the answer is it depends. So each approach has some advantages and disadvantages. Essentially, the skipgram approach works well when you only have a small corpus and therefore terms that are more rare, because the way we generate the training data, we generate a lot more training data out of the input. CBOW, on the other hand, has a better accuracy for frequent words and is a lot faster to train. There are a few more tricks. Instead of just doing the plain training, like I showed you, people have done various optimizations on the training. For example, one idea is to add bigrams to the corpus as single terms. For example, terms like New York or Elvis Presley. In the simple approach, we would always split them up into individual words. But you can do some pre-processing and realize this is standard NLP technique to find out that New York in this form very often appears together. Then we add this as a single input for the neural network. So we have new, we have York, and we also have New York as one hot vector input. Similarly, there are tricks for dealing with high frequency words called subsampling, and some tricks to speed up the training using negative sampling. So in this case, we don't try to update all the weights all the time, but sort of pick some samples to decide which weights to update. In the readings, you can see a bit more detail on how this works. But the point is, these are optimizations to improve the accuracy of the vectors and also the time you need for training. Okay, time for a quick break. And in the next part, we'll look at how to use this in practice using the Spacey library. See you then.